So we're going to start on Berger's equation. So this is the final topic, and it's a different equation, but it's the same ideas we've seen before. So, not identical, but there's nothing really radically new here. So let's just start with an introduction. So remember when we went back to the very first equation we considered, this traffic flow problem, we found that it had shocks. And we could get rid of that. One of the exercises you did was to get rid of the shock by adding this term in here, which is some kind of diffusion. So basically, as it starts to get towards a shock, this term, we keep mu small. So as we start to approach a shock, this term here, which is normally small, suddenly starts to become large because we get a very large change in the row. Okay, so the curvature goes up, and that corrects it and smooths it out. You actually saw you got the same solutions. All right, so what we do, Berger's equation is just the sort of simplest version of this. It's dt u, okay, c becomes u, plus u times dxu is equal to mu dx squared u. Okay, and it was actually, Berger was studying turbulence or something like that in fluids. He came up with this equation, but this equation is to try and model that. So, and we still don't understand a lot about turbulence, and we're not fully sure about where to go from Berger's equation, and all these nonlinear equations. But let's have a look at this equation. So what are we going to do? We're going to do three things. We're going to find the travelling wave solution. We're going to solve numerically, and we're going to use our split-step spectral method. And you actually have already solved this equation numerically, so you can see this is going to be dead easy to solve. And three, we're going to find an analytic solution. Now, it's interesting in these, one of the features of these problems is the analytic solution is probably more complicated to program and to use than the numerical solution, and less general.